Hi, this is Professor Fernandez. We are talking here about video 2 in lesson 7. This topic is about limits yielding infinity. So in the previous video, video 7.1, this was about limits as x approaches infinity. So you might want to review that just because we talked in that video about some of the basics about what infinity is, why we don't use left and right limits when infinity is involved, and also about horizontal asymptotes. This is a video about limits yielding infinity. So each of these limits is gonna give us some version of infinity, plus or minus infinity, plus or minus infinity, plus or minus infinity. So we kind of know the answers right away, but it's the process and also the concepts that we're going to review that will get us to those determinations. So let's look at the first limit. This is the function 1 over x squared, and we're taking x to 0. Notice first that x equals 0 is where the denominator is 0. So I can't just substitute in x equals 0, which is what I always suggest that you try first when evaluating a limit. If you can, right? You can't substitute infinity, for example. We talked about that in the previous video. So we can't substitute x equals 0. It's not in the domain of the function. So I have to find this limit some other way. There's no simplification I can do. There's no rationalization. So I could try a table, right? A table and a graph. Those are two things that would help. So 1 over x squared. So here's 0, and I'm just going to put a dash because the function is not defined there. So I'm just going to try a few values that are close to 0 on either side. How about 0.1? And so that's negative. And how about 0.1 over here? 0.1 is 1/10. So let's see what happens if I substitute in 1/10 for x. First, I would have to square it, so I would get 1 over 100. And then I'm taking 1 and I'm dividing it by 1 over 100, which is the same as multiplying it by the reciprocal of 1 over 100. So the answer is 100. So notice that 1 over 100 equals 100. So I've written it in this very specific form to make our lives easier for what you will see in a minute. Okay, so I'm going to put over here, and one thing I did is if I had made this negative, because of the square, right, that would not have mattered. I would still have gotten a positive 1 over 100. So I have this benefit here that at x equals negative 0.1, 1 over x squared is 100. At x equals positive 0.1, 1 over x squared is also 100. All right, so what if I did negative 0.01? A little closer to 0. This is a 1 in the, let's see, tenths, hundredths place. So this is x equals 1 over 100. So I'm going to go back over here and put a 0 there. I'm squaring it. So I put, let's see, I need 4 zeros. 1, 2, 3, 4. All right, so I square 100 and I get 10,000. Put a little comma there and make sure I have the right number of zeros. So then 1 over 10,000, 1 over 10,000. When I'm dividing by that, I'm multiplying by 10,000. Great. So then over here, 10,000. Add some zeros here. 10,000. Okay. So I get 10,000. Right. That is what the output is. Doesn't matter if it's plus or minus again because it's a square. So the same thing happens over here with 0.01. I get 10,000. Okay, so I hope you can see what's happening, and that's why I've written it in this way on the left-hand side. If I keep adding a 0 here, if I did 0.001, negative 0.001, okay, I'm going to keep adding zeros, right? And so what's happening to my number? As I approach 0 from either side, my number is increasing and increasing and increasing. And because I keep adding zeros and zeros and zeros, I'm going to keep increasing without bound. So what this table is telling me is that this limit is actually going off to infinity. So in our course, we say that this limit does not exist, and then we put the information about why it doesn't exist. In this particular case, it doesn't exist because it goes off to an infinity, specifically positive infinity. So there it is. That's the infinity that we said would be yielded by the calculation in this video, this topic. Okay, so you can confirm this. Again, if you graph this function, 1 over x squared, we did this in the previous video, talked about it at least, you can see that as x goes to 0, whether you're approaching from the right or from the left, the function is shooting off to positive infinity. Great time to talk about vertical asymptotes, because if it happens that you take a limit as x approaches a number of a function and you obtain an infinity, positive infinity or negative infinity, then what you have is a vertical asymptote at that x value. So we can say that x equals 0 is a vertical asymptote of y equals 1 over x squared, right? The function in this example. Okay, so let's try this again for a different example. So how about this example in the middle here? How about the function x divided by x minus 1? In the previous video, we talked about taking this limit as x goes to infinity, right? And I talked about a couple of techniques that you could use, a growth argument and also dividing by the highest power of x in the denominator. That worked pretty well in that video, but we're not taking the limit as x goes to infinity anymore. This is now limit as x goes to 1. We'll do the same thing we normally do. What if we try to substitute in x equals 1, right? This would give us 1 over 1 minus 1. You see the problem, we're dividing by 0. So that doesn't work, can't do that. Back to the drawing board. Our usual options, graph, table, algebraic techniques, or perhaps some other way to calculate the limit that we haven't thought of. But what we're going to do here is realize one thing, okay? This is a two-sided limit. So in order for the two-sided limit to exist, as we've talked about earlier in the series, each one-sided limit has to exist, and they both have to equal the same number. So let's investigate the one-sided limit as x goes to 1 from the right of this function. At this point, we can make a table again, or we can just kind of think this out. So I'm going to introduce you to some new notation here. So x goes to 1 from the right. Here's an x. So how about I put 1 from the right? What in the world does this mean, right? This means, for all practical purposes, the number closest to 1 that you can possibly imagine, but greater than 1. Okay, so think of it that way. And therefore, the same thing happens over here. Here's an x. X is going to 1 from the right. So I'm going to write 1 from the right minus 1. Okay, so now we'll do some I don't even know what to call this, superscript math or something. 1 from the right minus 1. In other words, take a number that is very, very, very close to 1, but bigger than it, and subtract 1. What you're going to get is a number that's very, very close to 0, but slightly positive, right? Because 1 from the right could be like 1.00000, like a billion zeros, and then a 1. That is a number that's very close to 1, but bigger than 1. Okay, so the denominator is like 0 plus slightly positive number, and the numerator is 1 plus, a number that's very close to 1 but to the right of 1. Okay, so you can see that this is still a number, but it is a number that is positive, right? So both numerator and denominator are positive. So our conclusion, and before I say that, as we've seen before with the limits that we did, specifically this one here, but not exactly. If x goes to 0 and I have 1 over x, in this case we had x squared, then what I get is a very, very large number because I'm taking the reciprocal of 0, right? So limit as x goes to 0 of 1 over x does not exist, but is actually infinity. And again, if you just make a little table, you can convince yourself of that. If x is 0.1, that's 1/10. 1 over x is the reciprocal, 10. If x is 0.01, that's 1 over 100. 1 over x is the reciprocal, which is 100. Okay, so as you keep getting closer to 0, you keep getting larger and larger. So you go off to positive infinity. This is from the right, I should add, because that's the limit that we're calculating. Okay, so this goes to positive infinity. So to remove the clutter here, what are we going to say? We are going to summarize this by saying that as I approach 1 from the right, for all the reasons we just talked about, this limit does not exist, and more specifically, grows without bound in the positive y direction. So it goes to positive infinity. Already, this is enough to tell us that this limit does not exist. Okay, we don't have to do anything else. But we might wonder Do we put positive infinity here? Do we put negative infinity? Do we just leave it blank? Well, the answer is we want to investigate the limit as x goes to 1 from the left. If we also get does not exist and positive infinity, then I would add positive infinity over here, because then at least you're giving the reader, whoever's going to read your work, information that says, you know what, this limit doesn't exist. It doesn't settle down to some y value, but at least both from the left and from the right, we know where it's going, right? The y values are increasing in the positive y direction without bound to positive infinity. Okay, so to do this similar calculation here, we'll speed things up a little bit. This would be 1 from the left. X goes to 1 from the left. This is an x, so that's 1 from the left. Divided by, that is also the same x. So 1 from the left minus 1. Okay, so now in the denominator, I have a number that's so close to 1, as close as you could possibly imagine, but to the left of 1. So like 0.99 bunch of a billion nines, right? So I'm going to get a number very close to 0 when I subtract 1, but negative, because again, I'm substituting in a number very, very close to 1, but less than 1. Okay, and then the numerator is still 1. So now I have a negative number here. I also, I have a positive number because this is 1, but very, very close to it from the left. So this is, again, back to our 0.99999 billion nines. The numerator is therefore positive. The denominator is a number slightly to the left of 0. It's negative. So positive divided by a negative. So this is a negative number. Okay, and it's effectively 1 over 0, quote unquote. And like we talked about before, that is driving us toward an infinity of some form. Because it's negative, we put these two pieces together, tells us that this limit is approaching negative infinity. So I'm going to declutter this here and then add that to our conclusion. So this limit also does not exist, and approaches minus infinity. Okay, so I'm going to go up here and then I'm going to erase this, right? Now we have all the information that we need. It turns out that as x goes to 1, this function does not go in the same direction. From the right, it goes off to positive infinity. From the left, it goes off to negative infinity. So I think the best answer is to just say the limit does not exist. Unlike over here, where this function, from both directions, from the left and from the right, went off to the same place, positive infinity, right? That's why these answers are slightly different. All right, and then to finish this up, let's look at part C here. There are two ways to do this. You might have seen that there's a difference of squares in the denominator, so I can factor that, right? X plus 2, x minus 2. And then you might have seen the numerator that each term has an x. Factor that out. Okay, let me just make things a little easier to read here. So x plus 2, and then divided by the factored denominator. So I could cancel these out in terms of the limit. And then my new limit would look a little simpler, x over x minus 2. And then you can see that this is very similar to the function we just did, except that there's a 2 in place of the 1, right? And we're approaching from the right. So we could make the same arguments here. If I substitute in x equals 2 plus, I think about what's happening to the numerator. It's approaching a number that's very, very close to 2, but larger than it. The denominator, when I subtract 2 from a number that's very, very close to 2, but to the right of it, I get something that's very, very close to 0, but positive. Okay, and the numerator is 2 plus. This is basically like what we had talked about before, with a number very close to 1, but larger than it, divided by a number very close to 0, but larger than it. This is a positive number. This is a positive number, so positive, great. And again, we are dividing by a very, very tiny number, so the result is going to be very large. So we think that this is going to approach infinity. So it does not exist, but we have some information, more information to give, so that the function is approaching positive infinity. All right, I did this with factoring. I just want to take 30 seconds and show you how you could reach the same conclusion without factoring, right? Perhaps you didn't see the difference of squares in the denominator, or somehow didn't factor. doesn't matter because you could make the same sort of argument that we just did that I erased a minute ago. You could say, okay, so as x goes to 2 from the right, what happens to the numerator? Where I get 2 from the right squared plus 2 times 2 from the right. Denominator, I get 2 from the right squared minus 4. And so this is my way of showing you yet another, cool thing that you might want to try to do with limits sometimes. And now I just do the math. So 2 squared is 4, a number very, 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 very close to 2, so close, right, that it's basically 2. When I square it is also 4. That's going to be very close to 4 and slightly larger than it. So minus 2 times 2 plus, so that goes, plus. Plus 2 times 2 plus, that's another 4 plus. Divided by denominator, we have 2 plus squared, that's 4 plus, 2 squared, 4. And then minus 4. So again, here we get 8 plus over 0 plus. In other words, this limit is going to approach a number that looks kind of like very, very close to 8 divided by a number that's very, very close to 0. But both of them are to the right of these numbers. Once again, this is a positive number, and we're dividing by something that's getting very, very small. So the outcome gets very, very large. So same conclusion, right? The limit does not exist. However, the y values tend to positive infinity. Great, so variety of ways that you could approach these limits. And like I said before, if you get to the point where you evaluate the limit as x goes to a number and you get some form of infinity, as we did here and here, then that tells you that the functions have vertical asymptotes. So for sure, 1 over x squared has a vertical asymptote at x equals 0. And then also, the function, this big blob over here has a vertical asymptote at x equals 2 because we found the limit, doesn't matter that it's from the right, and we obtained information about it flying off to infinity. Okay, great. By the way, for that matter, this function also in the middle has a vertical asymptote at x equals 1, right? From the right-hand side, flies off to infinity. From the left-hand side, flies off to minus infinity. So this one too has a vertical asymptote, at x equals 1. Great. So we found 3 vertical asymptotes. We talked about a bunch of different ways to investigate these limits. So I'll see you in the next video.